Good morning, good afternoon, good evening to the audience of NanoScientific Symposium Asia. I'd like to present our work on nanostructured nanomaterials and biomedical applications. I'm a professor at the University of Tennessee and group leader at Oak Ridge National Lab. My group does a lot of work on interfacial chemistry, nanostructuring, polymer brushes, and 3D printing. I'm also the editor-in-chief of MRS Communications, and I invite you to send your best papers. Now, the area of polymer stat interfaces and colloidal phenomena spans the gamut of surface functionalization, aggregation, ordering in colloidal particles, polymer brushes, membranes, and ordered multilayers, where the dimensions and the particle size are similar to what we observe with carbon-based, metal oxide, semiconductor nanoparticles, and so on. The way we can order films and structures at interfaces, it can be based on multi-layer deposition using electrostatic layer-by-layer deposition, Langmuir-Blodgett films, electrodeposition, polymer brush grafting by surface-initiated polymerization, chemisorption, and even vapor and chemical and physical vapor deposition. Now, we have done a lot of work on the synthesis of conducting semiconducting polymers, dendrimers, ladder polymers, where we have high electro-optical functionality. Also, we have done work related to hybrid nanoparticle systems, where metal to semiconducting nanoparticles can be grafted with dendrons that display energy transport and charge transfer properties that can be mediated by the microstructure. Lately, we have been working on templated natty polymers, where the template that can be complex with a metal serves as a macro initiator for growing polymers. In this case, we've done it a lot with ATRP as well as polymer expansions based on polycaprolactone anionic or living polymerization methods. Now, grafting of polymer brushes and surfaces can be done by surface-initiated polymerization, utilizing chemisorb initiators as well as layer-by-layer deposited macro initiators using polyelectrolytes as well as electropolymerization. And then lastly, some of our work involved the formation of nanostructured layers through polyelectrolyte self-assembly based on oppositely charged polyelectrolytes that can be deposited alternately on flat surfaces to particle and even hollow shell and core shell particle geometries. But today I'm going to focus on two themes. The first is that of using colloidal nanosphere lithography for applications in sensor, biosensor, and virus assemblies. And then the last part will focus on graphene and graphene oxide for antimicrobial, antipathogenic applications. In the past, we have demonstrated that latex sphere particles of polystyrene can be deposited on surfaces as two-dimensional arrays, which have a hexagonally packed structure as expected, to show very interesting templates for the deposition or rather electrodeposition of conducting polymers. In this first paper, we demonstrated that the potentiostatic deposition of polypyrrole on these templates results in beehive-like structures, half-dome and full-dome structures. These particles can in fact be harvested from these surfaces to produce micro or hollow shell capsules. Now, we have demonstrated that by utilizing different types of electropolymerizable monomers, cross-linkers, we can get very robust conducting polymer arrays, as shown here, where the templates of the original polystyrene particles can be removed by dissolution with THF. And in this case, we deposited these conducting polymers using cyclic voltammetry. On the other hand, we can play around with various geometries of grafting multi-material systems. In this case, the conducting polymer was first deposited as arrays. However, we can backfill the empty spaces on those arrays with an initiator for atom transfer radical polymerization, or ATRP, and then grafting polymer brushes with poly-NiPAM. Now, this differentiation is dramatically seen by the conducting AFM micrograph, showing a green color representing that of the conducting polymer material and a blue color representing that of the grafted polymer brush. We have then demonstrated the possibility of actually grafting the polymer brushes themselves on these conducting polymers by the use of electropolymerizable conducting macroinitiators for ATRP, or RAF, which stands for reversible addition fragmentation chain transfer, or RAF polymerization, and then the use of metathesis macroinitiator systems. The result is we can then graft the polymer brushes directly on top of the conducting polymers, as shown here. However, we still have the ability to backfill the holes with the macroinitiators that were deposited by self-assembly, and therefore we can have a binary to ternary composition of the two polymer brushes and the conducting polymer pattern array substrate. Now, turning to enzymes, or the inspiration of enzymes for building in selectivity and sensitivity in these films. Enzymes are, of course, well known for their binding kinetics that are very specific, with a rate model, occupational model, or induced fit model as far as action of true enzyme. And in terms of dimension, they are akin to dendrimers in terms of their size, microstructure, and topology. Now, the importance of enzymes are well demonstrated with membrane proteins, which is able to regulate ion transport and therefore vital towards the health of the cell. However, enzymes can be found in many parts of human body or physiology, where the specificity is similar to that of a lock and key mechanism. The key, or the substrate, is very specific for that lock or enzyme, and therefore action can be induced by the presence of these highly specific interactions. So a well-known approach called molecular imprinting polymerization methods takes advantage of the interaction between monomers for vinyl polymerization and the analyte or substrate. Subsequent cross-linking results in cavities that are very specific for the original template, as shown here, which means you have very high binding constants for their assay studies. And this type of specificity can be artificially made on films as well. So in our case, we focused on building complexes of the template, analyte, and electropolymerizable monomer. Electropolymerizing this complex on a variety of surfaces enable us to demonstrate these high binding kinetics between the original template and the artificially produced cavities. And in fact, this type of complex is almost like an analyte core dendrimer in terms of dimension. Now, utilizing substrates such as in gold, which is used for surface plasmon resonance spectroscopy methods, can subsequently be demonstrated as a sensitive element for the buildup of sensor devices. So an SPR sensor will allow us to observe this binding assay on these artificial enzymes that are bound on substrates. So we first demonstrated this with a variety of drugs, naproxen, theophylline, theobramine, paracetamol, caffeine. And as you can see here, the similarity between the theophylline, theobramine, and caffeine really shows the high selectivity when you build in the chemistry to produce that lock, quote unquote, from the key template. So utilizing monomers of tertiafine, we then pre-complex it with the theophylline template, for example, and then electropolymerizing it as films on the gold substrate produces cavities that are very specific for that original template. So the question is, if we vary the original template, should we see specific selectivities for those templates that were used? And the answer is yes. As you can see here on the binding assays as observed by SPR reflectivity measurements, we get very high selectivity or sensitivity when we use naproxen, theophylline, and paracetamol as templates, whereas the other analytes or drugs have low sensitivity. And thus, this type of exercise can actually be extended to a number of molecular systems. So here, we've demonstrated that a serine analog, dopamine, TNT analog, bisphenol A, melamine, morphine, aspartame have this built-in specificity when this particular approach was used. The question is, can we envision combining the colloidal nanosphere lithography method of producing arrays with the cavities that can be produced by this molecular imprinting approach? The answer, of course, is yes. Here, we demonstrate that if we use norepinephrine and its 2 enantiomers as templates, we can display chiral selectivity, let's say with the tertiafine monomer, where the electropolymerized material is deposited on a quartz crystal microbalance gold substrates. So in this case, this was done by cyclic voltammetry. So in these binding assay studies, the chiral selectivity was demonstrated by the high frequency shift. That is, if we look at the assay, the a large delta in frequency indicates the binding of the drug or this analyte on the MIP produced substrate. So between the 2 enantiomers, we get, of course, opposite effect. That is, if we use one enantiomer, the other enantiomer is not so selective. On the other hand, if we reverse the role, then we observe the same strong effect of differentiation. Also, when we expose it to other drugs such as naproxen or dopamine, we get low sensitivity for those non-original templated analytes. So this paper was published indicating that chiral selectivity was easily demonstrated on templated arrays as well as MIP. Now, turning towards virus assemblies, we have done a lot of work with the Steinmetz group now at UC San Diego, where we look at the cowpea mosaic virus or CPMV and its functionalization with dendrons and dendrimers to produce highly loaded virus assemblies with dendrons that can be used for attachment of drugs or complexation of drugs, and its use in theranostic as well as anti-cancer drug applications. So in this paper that we published, we showed that the modification of the CPMV with dendrons results in a high loading of the drug represented by PS, and then showing a high cell motility or destruction with the presence of the modified dendron surface. So in this study, the dendron or the attachment of the dendron to the CPMV was done by modifying the amine groups towards click chemistry with the azide and the acetylene. The result is the presence of the carboxylic acid allows us to bind the zinc-based drug and demonstrate it for delivery as well as the toxicity against cancer cells. So first, this was demonstrated by electrophoresis assay and direct visualization of the modified virus using TEM. However, the efficacy for cancer cell destruction was shown by the live cell dead cell assay comparison. In this case, the CPMV virus alone did not have as high as cancer cell death as with the drug-loaded dendron-modified CPMV. And so this type of assay shows that virus cells can be modified towards high increasing binding as well as toxicity against cancer cell lines. Now we can use these viruses also as nanoparticles, as shown here. The symmetric virus by TEM has a net charge. That charge can be utilized to bind on polyelectrolyte layers as well as binding on arrays of colloidal field nanolithography access templates. The result is we can get this whole arrays and have the CPMV virus closer to the periphery. And in fact, these arrays can be created as freestanding films, which can be lifted or removed so that you can get virus assemblies that are highly ordered and loaded for, let's say, therapeutic applications. Now, let me then turn to the last topic of our talk, which is graphene and its use as antimicrobial agents. Graphene is a highly sought after nanomaterial. The cost is actually going down. Graphene and some of its outstanding properties includes conductivity, semiconducting properties, effective moisture barrier properties, as well as high thermomechanical properties when properly oriented. And its use is well known in solid-state devices, flexible electronics, actuators, electrochromic devices, etc. What is not so well known is its ability to kill bacteria or other pathogens when properly oriented or in high concentrations. So, for example, the preparation of graphene oxide can be accessed by micromechanical cleavage of graphite, carbon segregation, or metal catalyzed deposition on surfaces, step-by-step synthesis. However, the most commercially viable method is based on exfoliation and breakup of graphite or graphite sheets into individual graphene particles that can be stabilized by the presence of surfactants. And in fact, we have done a lot of work on graphene. In this case, we actually use a polymer matrix or PVK to assist in the deposition of the graphene on surfaces, as well as its ability to kill bacteria in solutions. So in the first part here, we show you that the combination of polyvinyl carbazole and graphene oxide produces graphene oxide that has a good monodispersity or polydispersity and well soluble in a variety of solvents. So utilizing solutions or films of this PVK graphene oxide combination can perhaps be useful for antibacterial studies, as I'll show you in a little while. So in this case, the graphene oxide PVK, PVK control was differentiated in terms of its optical density when it comes to the presence of bacteria. So from the graph, it simply shows that the presence of graphene oxide, or even better, the combination of graphene oxide and PVK kills more bacteria because of the higher optical density in solution. However, another way to observe this dead bacteria is through live cell, dead cell assay, similar to what I've shown earlier with the arrays, as well as the viruses. So in this case, the live cell did not show much of the differentiation. However, when we turn to the treat-see fluorescence, we can see more dead bacteria in the presence of graphene oxide or graphene oxide PVK. Now, in another variation, we can compare the performance against gram-positive and gram-negative bacteria. Between E. coli and B. subtilis, it has shown the same or high toxicity. However, when it comes to exposure with fibroblast mammalian cells, it did not kill as much, up to 80% survivability. indicating that the graphene, PVK, or graphene presence is less harmful to mammalian cells. So, for example, we can see that in the fight against biofilm formation, the PVK-GO shows better properties against biofilm formation with respect to surfaces and competing against PVK and ITO, as shown in this AFM morphology. We can also combine graphene oxide with functionalization with EDTA, a high carboxylic acid functionality that is useful for chelating metals. And so demonstrating that graphene can chelate metals as well as display antimicrobial properties was published in this paper with carbon in 2014. So here we can see that the cell inactivation is displayed both on the graphene oxide and the EDTA graphene oxide test. However, its cytotoxicity against human cells, like the previous example, was shown to give high survivability. Now, to test the presence of graphene oxide in higher quantities on surfaces, we then deposited this graphene oxide using Langmuir blodgett film, produce 1 layer, 2 layers, and 3 layers. And so this assay, similar to the previous one with the live and dead cell assay, showed high toxicity with higher concentration of graphene oxide in 3 layers. And so this means that the exposure of more surfaces of graphene oxide produce more cell death. So in the future, we will be studying the quantification of the radical oxygen species present on this type of films. So with that, I'd like to thank you, and I'll be happy to answer questions. You may access me by email, rca41@case.edu. Thank you very much, and hope you have a good conference.